Good morning, everybody. My name is David Wavell. I'm the Business Development Lead for the ORCA Hub. So welcome to the first in a series of challenge information sessions being held this week. Just to let you know that this event is going to be recorded. It's going to be posted on our social media, on our website and our YouTube channel. So if that makes you uncomfortable for whatever reason, then please do what you need to do. So the purpose of these events this week is to provide you all with a little more information about the challenges that we have set out to solve in the extension of the ORCA Hub. Hopefully you all managed to attend the webinar on the 17th of June and got a flavour for what we've achieved so far and we're planning to do next across the whole of the Hub. However, this morning you're going to hear from Dr. Sen Wang, one of the academic leads, about how he and his team will work on multi-robot cooperation for remote subsea inspection and intervention. So Sen's going to present his work for about 20 minutes before we'll open up for a few minutes of questions at the end there. So hopefully you can all see my screen at the moment. So following this event and the others that we have this week, where you'll hear from the other academic leads, we're also going to be hosting a series of what are called AIM days in the first 2 weeks of August. And we'll be holding one of these AIM days for each of the challenges that we have. And the purpose of these is to give you an opportunity to speak one-to-one with the academics leading the work to discuss working on projects together related to their challenge. So if after hearing today's session, you're interested in discussing a project idea you might have, please get in touch with me. My email should be in the chat there. I'll post it again shortly as well. I'll send you a pro forma to complete, which will to outline your idea. We'll then use this to help us plan and prepare for our AIM day one-to-one with you. You can see the dates and the times of the AIM day on the AIM day of the screen there. I'll also share this in the post shortly. We'll also make it available on our website and social media channels with also details about how you can get involved. So at this point, I'm going to stop sharing my screen and I'm going to hand over to Sen for his presentation. So over to you, Sen.
Thanks. Thank you everyone coming over and joining us today. So my name is Sen Wang. I'm an associate professor in robotics and autonomous systems at Heriot-Watt University, and also I'm the lead of a Challenge 1 in the ORCA. So the Challenge 1 is all about the multi-robot cooperation for subsea remote inspection and intervention. So let me explain a bit of what we mean for this challenge. So this challenge, we really look at how to replace the cruise support vessel, which we really use a lot during the current situation for the offshore operation. So we want to replace this with more kind of like unmanned surface vessel plus ROV. So this will give us much better opportunities to eventually remote people from offshore operation to onshore remote operation. So this is going to improve all our safety, efficiency, and hopefully support all these net zero targets, everything. So this is going to be very challenging and interesting for us, because meanwhile, we also want to have a cloud platform, so we can really integrate all the data we collected and have AI or machine learning models deployed there and give us Tele-Presence capability. And meanwhile, also we can have the safety measures embedded in there when user doing the interaction and with the digital twin. So this is the joint challenge with Heriot-Watt University, University of Edinburgh, Imperial College London, and University of Liverpool, with all my colleagues here. So to working together to push this forward. So eventually, we really want to demonstrate this challenge in the offshore wind farm as use cases. So we identified 4 main technologies we think is really important. So as the pillars to eventually support these Challenge 1. So the first one is the coordination of unmanned surface vessel and ROV. So I think I want to quickly to review what we can achieve now. So some of you probably quite familiar if you joined the 17th information session. So, but let's just quickly understand what we can do and what we are missing. So what we can do now is we can quite reliably localize our robots or underwater vehicle using different sensor fusion solution. Okay, and based on that, we can repeatedly ask the ROV to go back to the key locations to do the inspection. So and this is great, and as a fundamental thing to support our underwater autonomy, which is showing more like planning and autonomous navigation. So the video showing on the left, so you can see the green is the trajectory, and each of the red circle is the waypoint we want the vehicle to go. And we can just assign one the waypoint, the robot gonna go and follow and do autonomously planning and navigation. So based on the localization and this planning capability, we can have a design trajectory. And if we know roughly the environment looks like, and ask the vehicle to follow and autonomously navigate around, and while doing all the inspection or other operation works. So this is one of the videos showing probably the work quite related to all these localization, planning, and autonomous navigation is for autonomous underwater inspection. So, and especially for the relatively close range inspection. So we have the vehicle drop in the water, the vehicle autonomously searching for the target, and using all the onboard sensors to build a map, and meanwhile to avoid all obstacles, and also doing the inspection in terms of collecting all the high resolution images, and also build this 3D map of the environment. So once finished all this autonomous operation, and then we come back, we have a high resolution data, we can build a much denser map. And this is the robot going and searching the path with the pattern, eventually finishing. So this is quite quick summarize of what we can do now. But what's really missing and in this challenge, what we're going to really look at for next step. So the very important one is really cooperative localization mapping of the USV and ROV, because when they're working together, so they need to have a kind of pattern to support each other with the tether of the ROV connected with the USV, because if everything we want to do is pretty much pushing to the autonomous operation. So we are starting to do a preliminary work, like showing on the right. For example, this black trajectory is the surface USV vessel, and so the red line here is showing the trajectory of the ROV when doing the inspection. So we need really to have algorithms and a system to understand how they collaborate together. So, and also we need to really look at real-time obstacle avoidance and planning with the surface vessel working close to the wind turbine in our use case. So how we want to have both the ROV and the USV has this real-time avoidance and also planning capabilities. So the multi-robot collaborative navigation and planning is definitely the main things to eventually support all the autonomous offshore operation. So that's why it's very big things. And the 3D exploration path generation or generates the path when we're doing this inspection, because it's going to be quite challenging environment when these two coming together with the tether management, all the things. We're starting to do this simulation now for this scope and based on our existing capability I showed before. So the next quite important technology we think, and at least is all the technology around one of the use cases, underwater inspection we really want to do. So I'm showing some of the current achievements we can do. So we can using a camera to extract and also collect very high resolution image with improved visibility. So I'll show you an example on the top left is a video. So as an example, we collect offshore and you can see, so the data collected, you can see much more improved resolution. This is very interesting for us because this can reduce the time for offshore operation and also improve the visibility for operators. Meanwhile, that means the robot have much more data to see what's around them and also doing the mapping and also doing the situational awareness. So after this, we can really using the current technology, what we can do to build dense map of the environment to do the inspection. This is very much based on the visual inspection, but for us, the new scope in this challenge or in this technology around is still one part is contactless inspection. So basically using vision, collecting all the videos, high resolution videos to really for the operators, for human, and also for the machine learning algorithms to understand what's happening for the ashes. So very important thing we explored and we really want to do and starting doing this is using 3D vision, is omnidirectional vision. I show you a video on the top right. You can see, so on the vehicle, we can have a full 360 vision. So this gives us a much better wide view of the image, which means, and when the operator sees the video, or when we're using this to train machine learning or deep learning algorithms, we can have much more data to ensure better coverage when doing the underwater inspection. Because we all know, if we go for one round of operation work, if we haven't got the data to cover everywhere, that's a really big issue. You have a salinity there. So that's why we really want to increase the data quality and the visibility. So, and then we can still continue doing the 3D inspection, right? So we can build a 3D dense map and more measure the dimensions. So one of the very important parts in this part for the underwater inspection is really doing a planning algorithm to ensure full inspection coverage. So which means once we go for one work, we really want to coverage everywhere we're interested in. We want to do inspection, but this is going to be autonomous systems, and we need to have a full understanding where we covered, where we haven't covered for the underwater inspection. This is going to be planning algorithms coupled with the previous ones I showed. So the next part is more like contact inspection. So this is especially doing non-destructive testing. So we have a collaboration work, and also so Fred from Imperial is leading the work to design and also manufacturing this marinized EMAS sensor. So egomagnetic acoustic transducer sensor. So we can use that sensors eventually deploy and also test our ROV and also underwater arm, and using this for NDE inspection. So this is the two new scopes we really want to focus in this underwater inspection technologies. So the next one is more focused on underwater intervention. So in the intervention, so currently what we can do, and we can use our system to stabilize the interaction with a physical structure, especially when we're facing disturbance, for example, the current, so the random current, and we can stabilize our vehicle and using the robot arm to do the contact with the asset. So, and also we can optimize the vehicle location for the maximum manipulability and also the force transmission. So we had a demonstration back in Blythe, so for the ORCA. So we had a vehicle dropping in the big tank, and we can send all the vehicle up the position and the pose through the 4G. And then we had a robotic arm and a steel platform in Edinburgh, in our lab, to simulate this motion and to do the inspection for the pipe. And also we have a simulator which can link as hardware in the loop to do this application. So we really target and want to do the demo is first for underwater asset cleaning, a biofouling cleaning, and the other is sensor deployment and combined with the EMAS sensor for the NDT. So the new scopes, what we really want to do in this underwater intervention, so it's very much around the contact aware remote manipulation. So we think contact aware is really important, especially look at the challenge we are looking at. It's going to be everything going to be remote. We're going to have the vehicle, the vessel, and the manipulator on the vehicle working remotely offshore, and we send all this information to the cloud, and the operator can interact there. That means for the operator, we really want to have a way to have a feeling when, especially doing the contact operation. So that's why we want to look at the haptic feedback based tele manipulation, which means the operator with the haptic devices can feel the force when the manipulator contact with the structure. So that's going to be remotely, you have a feeling what's the force applied there and how that's going to be. That's going to be ensure the safety for the interaction with the asset. So, and also we have vehicle manipulation control and time delay and disturbance, because this is really key when doing the remote operation, because everything going to be remotely operated. The time delay definitely going to be there. And also the disturbance, we need a vehicle to handle all these challenges. And the next is really underwater operation using underwater arm. So I'm showing one example here. And we have another Falcon vehicle, which recently attached with another big arm for underwater operation. So, but we start to using all this to do all the testing algorithm development. So we really want to look at how to using this to do the remote NDE and also clean the bow falling with a human in the loop. It's not everything autonomous when starting to do manipulation or doing the contact interaction with the asset, because we think this is for the benefit of the industry to really understand the safety. So that's why we want to have haptics and every time we work on the manipulation. So just a note for the previous one, the visual inspection, which just like no contact with asset. So that means we can do everything autonomously remotely. But for this underwater intervention, we really want to have a human in the loop. So the last one is the cloud and the remote operation. So what we can do now is we can stream all this full resolution 360 video, and for 4G or for other internet or Wi-Fi to everywhere, pretty much everywhere around the world. And we have a recent test with the US colleagues. They can operate our vehicle from the US, have the full real-time video and to understand what's happening and teleoperate it. And also we have a system to, based on the previous example I showed, autonomous inspection using all the vision and all the sensor fusion sonar to avoid obstacles. So that means we can have an operator window or operator system on the browser, and the user can just select high-level command to choose where to do the inspection, and with the full video and the map and also the vehicle location in a browser. So we demonstrated this for one of the UK festival event a few weeks ago, and with many users connected around the UK. So that means we have a capability to deploy these systems on the cloud platform using 4G or using Wi-Fi or other internet. So and it's kind of device and platform agnostic, because people can use different phones or laptops, because based on the browser to eventually to operate and also understand what the robot is doing. But what we really want to extend, and based on this technology for the cloud and the remote operation, is to really give the user a full understanding what's happening on the remote side. So when the robot is working on the site, when the user offshore office, what's really happening there. So one of the very important things I can mention for the manipulator is really have a haptics understanding. So one of the things we're gonna have a tactile sensing with the gloves, and a remote user can really understand what's the vehicle is doing there when have the contact. And also we're gonna have the cloud data learning and deploy machine learning models and training machine learning models as a whole pipeline on the cloud server. So, and one also very important things, we're gonna have a digital twin for the user interaction and also visualization and also the real data representation showing this. So safety, we think, is really crucial when we're doing this work. That's why we have Dr. Sen Wang from University of Liverpool leading the work, doing all the safety verification of this technology. And we're going to design a safety measures for the edge robot autonomy, which means on the local robot system, we're going to have safety measures there. And also we're going to have a safety measure designed on the cloud system. It's kind of 2 layers system. And also we're going to do a safety case for the perception of underwater vehicles, especially when they do the autonomous inspection, where we're going to format and also build this safety argument and also cases. So great, this is the review of these 4 main technology areas we're going to develop, and with a quick review of what we can do now. So I want to really highlight, so what's the challenge 1 demo going to look like. So we're going to focus on the user cases around offshore wind farm. This is the challenge 1 we're going to target on. We're not limited to that because the technology is very general. We can definitely use it for offshore oil, gas, and other sectors. But for the demonstration purposes, we're going to focus on the offshore wind farm. So around the inspection, so we're really going to have the USV and ROV for autonomous underwater inspection of offshore wind turbines. So we really want this to be as a demonstration offshore, eventually before the end of the ORCA extension period. The next is we want to have using the image sensor we built in ORCA and test that on the ROV and to do the underwater NDT. And this probably gonna happen in the tank. If we really have support from industry, we really want to push that also to the offshore. So in terms of the intervention, so we have 3 sub demos around this. One is the image sensor placement, scanning, and the removal from actual surface. So this is linked with the inspection. So and also the next is biofolding cleaning, using underwater. Using underwater assets. So because cleaning for us is quite important many times before doing NDT. So and also is haptic teleoperation for maintenance. So which means we're gonna have a remote manipulation capability, and for the operator we have haptic sensing, and we're operating that so remotely. So most of these things we're gonna have a remote monitoring and operation. So that means on the cloud side, so the user can be at home, can be in the office, eventually to monitoring and also interact with the platform, understand the data, and design the mission. So and as all the connection between all these several 5 use cases. So we really invite all the industrial partners and you guys to join us and also express interest and see how we can collaborate together, eventually demonstrate this technology. And I really hope this can be embedded in your use cases and to help you to solve some of the current challenges using robotics and AI. So that's me, and this is the team for the challenge 1. Thank you.
Thank you very much, Sen. Very interesting. If I could just ask you to stop sharing your screen, if that's okay.
Yeah. Yes.
So we've had a couple of questions in the chat, which is fantastic. So the first one is related to you talking about the EMAT sensor. So Mukeda, and apologies if I've mispronounced that, asked, how is the energy consumption of the EMAT equipment for ROV?
No, I think the current sensor, so Fred and the colleagues developed, they have a battery. The battery pack roughly this size. They can last for 2 hours for that battery. So if we connect with ROV, so I think so the power going to directly come from the ROV. We don't think the power going to be direct issue.
Perfect, thank you. Hopefully that answers your question. If you have any follow-on questions related to that, please put it into the chat there. There's been a couple of questions related to the haptic sensing, Sen. So first one is, what is haptic operation? And then another question around what haptic sensor will you plan to be using, Sen?
Okay, so I think this is a very interesting question because haptics is the one we haven't really used a lot in the previous work for the ORCA, but we gradually realized that's important for remote because many of the work period we do was not remote. So the haptics, so what we meant is eventually the user operator have a device at home or in the office. So when the arm especially have a contact interaction with arm with the structure, so the force on arm side or all the joints gonna feedback to the user interface. There's 2 devices we look at. One is more like a haptic device with joint you can control, and the other is gloves. So when you wear that, the sensors on that you can feel, and they give you a force sensing. So that means when the arm have a contact with the structure, you have a sensing how much the force is really there. Because for us, that's really important. If you just look at the video and you operate that, you have no idea what kind of force really applied there. So for us, this is going to help us to improve the safety when interacting with the structure. Hopefully that's useful information.
Do you have an idea of what type of haptic sensors you'll be using, Sen?
So why is the gloves? So we have a textile gloves. So the other one is a device I think Sufi and Zibin, the other colleagues, they are working on. So I'm not directly using that device. I can provide a bit more information later if you're interested.
Perfect. And there was a question around whether we'll be looking to transfer the work from ROV to AUV at any point.
So this is a very good question. So I think for the autonomy side, so pretty much is AUV for us now, because the tether for us mostly is just like transmitting data and also monitoring and diagnostic. So we don't really using that provide power for our current experiment. For the big ROV we use for the offshore, yes, that's provide power. I think as long as we can solve the power issue, there's a potential we can just convert the algorithm to the AUV side. So there's definitely for us is interest, and definitely is on our roadmap to move all this to the AUV side. But for now, we think there's more a smoother transition probably in this 9 months for this challenge to using the ROV, because that means it's much easier for us to monitoring what's really happening offshore, because that's very important. We want to have on the remote monitoring continuously video and also data, because if it's AUV, so we're gonna lose, probably have very limited information due to communication constraints. So that's why the benefit of why we want to start with ROV, to really have the relatively real time or live data and also control if anything emergency happening. So, but definitely it's the interest for us and our roadmap to move to the AUV gradually.
So that actually leads quite nicely onto a next question here, Sen. So in terms of communication, what is your view of the requirements to achieve the teleoperation and digital twin application?
Yeah, so this is a very good question, and also we are also learning this, right? So this is the challenge we're gonna do, and we have some kind of feeling doing our current work, especially the remote operation. I would say actually, if we handle well, don't send all the raw data and just have a select data, so the current 4G is enough, at least based on our understanding. So that's why sometimes you're probably gonna have kind of like blogs or suddenly like internet like issues. That's why we want to have this disturbance and the time delay control on the local system, on the local robot. We improve as I mentioned, we improve the autonomy side, but also we have the control with the time delay and the disturbance on the local robots. It's not on the cloud. That means if we don't have a user control command, that means the robot is going to try to handle itself, have the delayed control. And generally, I think for the 4G and what we have for our application, it should be enough as long as we're starting to learning this. But as I said, so this is learning experience also for us eventually, and also quite related to application, I believe. So it depends on which data you really want to send out real time for the control.
Thanks, Sen. So there are a few more questions in the chat there, but we've actually reached our time here. So what I think we'll do is we'll maybe answer one more, and then we'll look at the questions and we'll address them and send the answers out to everybody after the event. So just very quickly on the last one. So what type of tool are you going to be using for your cleaning and for your cleaning, Sen? Is it going to be a brush? Is it going to be a jet?
Yeah. So the cleaning is an interesting one. So we've been looking quite a while. So the first one we're going to do is using brush. So we're going to use a brush and so from the arm. So that means we can design using the manipulator, design the trajectory and using that to clean. So we started to look at also using the jet, so the pressure jet. So but we haven't really have a, but if you are interested about this, I'm really more than happy to discuss this and explore how we can collaborate together.
Lovely, thanks, Sen. So there are a few more questions in the chat there, which unfortunately we won't get time to address right now. Like I said, we will address them independently and provide answers to them to everybody. So thank you very much, everybody, for attending this morning. Hopefully you can make the other webinars each morning this week. And remember, if you're interested in getting involved in this particular challenge, please get in touch with me. My email is d.wavel@hw.ac.uk, and we can look to have one-to-one sessions at the AIM Day, which for Sen will be on the 3rd of August. So we can talk directly then. Thank you very much, everybody. That's the end of today, and hopefully we'll see you all tomorrow.
Thank you, everyone.